Have you ever stopped to consider the sheer wonder packed into a tiny tube of superglue? It sits there, unassuming in your kitchen drawer or workshop. Yet, within that small container lies a chemical marvel, a testament to human ingenuity and the fascinating laws of chemistry. We reach for it to mend a broken teacup, a child's favorite toy, or even a piece of essential equipment. It's a quick fix, a silent hero in our daily lives, performing small miracles of adhesion. This isn't magic, though it often feels like it. It's science, a beautiful dance of molecules that we can explore together. Think about the last time you used it. That instant bond, that restoration of wholeness. It's quite something, isn't it? The power of superglue is almost legendary. A single drop can hold surprising weight, defying gravity and our expectations. This isn't just about sticking two surfaces together, it's about creating a new unified whole from separate parts. So let us embark on this journey of discovery, to unveil the sticky science that makes superglue one of the most versatile and astonishing adhesives known to humankind. At the heart of superglue's power is a special kind of molecule. This molecule is called cyanoacrylate. That might sound like a big, complicated word, but think of it like this: it's the main building block. Imagine tiny individual Lego bricks, all identical. These are the cyanoacrylate molecules, or monomers. Monomer means one part. In their liquid form inside the tube, these monomers are separate, floating around waiting for their cue. They are small, nimble, and eager to connect, but they need a trigger, a signal to start their construction project. These cyanoacrylate monomers are the stars of our show. Each one is a relatively simple structure, but it possesses a unique characteristic: it's highly reactive. The specific arrangement of atoms within the cyanoacrylate molecule makes it unstable in certain conditions, particularly when it encounters even the slightest trace of moisture. The stability within the tube is maintained by a tiny amount of acid, an inhibitor, which prevents these eager monomers from linking up prematurely. When you squeeze that drop of superglue out of the tube, you're releasing these tiny architects into a new environment. They are no longer protected by the acidic stabilizer. Instead, they are exposed to the world, and more importantly, to the minute amounts of water vapor that are almost always present on surfaces and in the air. Now let's talk about that crucial trigger: water. It might seem strange that water, often the enemy of adhesion for other types of glues, is the key initiator for superglue. But it's true. Even the tiniest invisible film of moisture present on almost any surface, or even in the air itself, is enough to start the process. This moisture contains hydroxyl ions, which are like little chemical sparks. When the cyanoacrylate monomers come into contact with these hydroxyl ions, a rapid chemical reaction is initiated. This is the moment the monomers have been waiting for, the signal to begin their transformation from a liquid into a solid. Think of it like a line of dominoes. The hydroxyl ion from water is the finger that gently taps the first domino. Once that first cyanoacrylate monomer is activated, it becomes highly reactive itself. It quickly seeks out another monomer, and then another, and another. This is not a slow, leisurely process. It's a cascade, an incredibly fast chain reaction. The presence of water, even in microscopic quantities, is the gatekeeper that unleashes the bonding power of superglue. This is why superglue can sometimes bond to your skin so quickly, as skin naturally has a thin layer of moisture. Once that first cyanoacrylate monomer is activated by moisture, it undergoes a profound change. It becomes eager to connect with its neighbors. This process is called polymerization. Poly means many, and mer means parts. So, polymerization is the process of many single parts, monomers, joining together to form long chains, polymers. Imagine each monomer as a person holding hands with two others. When the reaction starts, one monomer grabs the hand of another, which then grabs another, and so on. Very quickly, long chains of interconnected monomers are formed. These chains are the backbone of superglue's strength. This chain reaction is incredibly efficient and astonishingly fast. It's not just one chain forming, but millions upon millions of them, all growing simultaneously and intertwining with each other. This rapid formation of a dense network of polymer chains is what causes the liquid glue to solidify almost instantly. It's like a microscopic construction crew working at lightning speed, laying down a framework of incredible strength and rigidity. These newly formed polymer chains are long, strong, and tangled, creating a solid material where there was once a liquid. Section 5. A molecular embrace, how superglue grips. So, we have these long, strong polymer chains forming rapidly, but how exactly do they stick to the surfaces we're trying to join? It's not just about the chains filling gaps, there are also powerful attractive forces at play between the polymer chains and the atoms of the material itself. These are known as adhesive forces. Think of it like tiny magnets. The polymer chains have parts that are attracted to parts of the surface material. This attraction helps to hold the glue firmly in place, creating a bond that is more than just a mechanical interlock. It's a true molecular embrace. These attractive forces are often van der Waals forces, which are weak short-range attractions that occur between all molecules. Section 6. The strength of 1,000 threads. Understanding bond power. The strength of a superglue bond can be truly astonishing. We often see demonstrations where a tiny amount of glue supports a heavy weight. This strength comes from the collective power of those millions of intertwined polymer chains and their tenacious grip on the bonded surfaces. Imagine each polymer chain as a single, incredibly thin thread. Individually, a thread might be easy to break, but weave thousands, even millions of these threads together into a dense mat, and you create something remarkably strong and resilient. This is precisely what happens at the microscopic level when superglue cures. The type of strength superglue excels at is tensile strength, its resistance to being pulled apart. When you try to pull two superglued objects directly away from each other, you are attempting to break those countless polymer chains or detach them from the surfaces. Section 7. Not a universal fix. The limits of cyanoacrylate. Despite its amazing abilities, superglue is not a magical solution for every bonding task. It has its limitations, and understanding these is just as important as appreciating its strengths. One major limitation is its performance with certain types of materials. For instance, superglue struggles to bond well with very smooth, non-porous plastics like polyethylene or polypropylene, the kinds often used for food containers or plastic bags. These plastics have very low surface energy, meaning the glue doesn't wet them well, and the attractive forces are much weaker. Another consideration is temperature. While superglue bonds are strong at room temperature, they can become brittle at very low temperatures and can weaken significantly at high temperatures, typically above 80 degrees Celsius, 175 degrees Fahrenheit, or so. The polymer chains can lose their rigidity or even begin to break down under extreme heat. This means superglue might not be the best choice for items that will be exposed to ovens, freezers, or rapid temperature cycling. Similarly, prolonged exposure to moisture after curing can, over time, degrade the bond, especially if the bond is under stress. While moisture initiates the cure, constant soaking can eventually undermine its integrity. Superglue also creates a very rigid bond. Section 8. From fingers to forensics. Surprising superglue stories. Superglue or cyanoacrylate has surprising applications beyond household repairs. It bonds skin, leading to medical uses. During the Vietnam War, medics used it to seal wounds. Today, doctors use medical-grade adhesives for surgeries. It's also used in forensic science to reveal fingerprints. Section 9. The universe in a tube. A final sticky thought. So, the next time you reach for that little tube of superglue, take a moment. Pause and reflect on the incredible journey of science and discovery contained within. It's not just a sticky liquid, it's a carefully engineered chemical system. It's a collection of tiny molecular architects, the cyanoacrylate monomers, patiently waiting for their cue. That cue, the gentle touch of moisture, unleashes a cascade of activity, a rapid-fire polymerization that builds strong, intricate polymer chains at the nanoscale, bridging gaps and binding surfaces with astonishing tenacity. It's a miniature marvel of chemical engineering in your hand. Consider the journey of its discovery. Cyanoacrylates were first synthesized in 1942 by Dr. Harry Coover at Eastman Kodak. He was actually searching for materials to make clear plastic gun sights during World War II. Initially, the extreme stickiness of cyanoacrylates was seen as a nuisance, a problem because it bonded to everything it touched. It wasn't until years later, in 1951, that Coover and his colleague Fred Joyner rediscovered the compounds and recognized their potential as a powerful adhesive. The first commercial superglue, Eastman No. 910, hit the market in 1958, and the rest, as they say, is history. A serendipitous discovery born from a different quest.